Time stepping affects computational cost a lot, and computational cost is always the constraint you need to take care when you get the allocated computational resource to run your job. So you always want to keep the computational cost to be small, or we say computationally light. In WRF, it is good. So consider the case of domain nesting. You have a fine grid, which has a final resolution here. The grid is visualized, and it is corresponding to a smaller area of the coarse grid. And as you see, one cell in the coarse grid corresponds to 9 cells in the fine grid. This is the usual practice. In WRF, we are free to use a smaller time step for the fine grid. And for the coarse grid, using the proportionality relationship, you can use a larger time step. And in WRF, you can configure WRF to use a larger time step for the coarse grid. Here, the spatial resolution is 3 times coarser, so the time step can be 3 times larger. This is good. But for the open source implementation of MPAS, it has already done a very good job in the spatial discretization, allowing you to have smooth resolution transition. But in that implementation, it supports only using a uniform time step for the whole mesh. So you will see that it will incur computational costs that may be considered unnecessary and you may want to save. And let me go back to this slide later. So the situation is like this. In unstructured mesh, you have both big cell like this, usually hexagonal, and smaller cells, and even smaller cells in the same grid. So for stability condition, when you determine the single time step length to use, the constraint is on the finest grid spacing. You need to take this short distance, multiply it, express it in km, multiply it by the factor 6 seconds per km, and then result in a short time step. And the software only supports using the same time step, no matter the cell is small or big. So you spend computational cost in using time step to do the time integration for small cell and also bigger cell and also even bigger cell. So for this cell, the stability condition actually allow it to use a bigger time step. So it is up to the software implementation to implement it or not, and also it needs some tricks in the implementation. So what we did in the last few years is to try to implement this. So in the CPAS version that modified the open source MPAS, we implemented jumping step for bigger cells like this. So here, 1 computation step instead of 2, and also like this. And for even bigger cells, 1 computational step instead of 4. So this saves a lot of computational resources. And that is what we arrive, and we put the program to the high performance compute behind the CPAS website. So as you run job, where we are using this, what we say, hierarchical time stepping to save computational time so that your job can finish in time as you have already experienced. So going back, few more difficult things I need to mention. In MPAS, the solver is actually different in the horizontal direction and the vertical direction. The implementation for solving the vertical direction is actually implicit. So as you have already been shown, if you remember the drawing that stacking up the vertical layers near the Earth's surface, the delta C, the vertical spacing is actually very small. And then going up, bigger and bigger. But we are still using time step that is quite large relative to that vertical spacing. And it doesn't harm because the solver uses an implicit scheme in the vertical direction. So the stability condition applies to the horizontal cell spacing only. And the implementation of time integration implemented in MPAS is actually a more complicated or higher order numerical scheme called the rush cutter scheme. And it has some more details in the actual computation steps. And it has advantage that the order of accuracy is higher, so the resulting error is smaller, and also the stability condition is a little bit relaxed with the Coulomb condition. Instead of being exactly 1, it is somewhat larger than 1, but it is still of the order of magnitude of 1. So this is some mathematical details. Okay, going forward. So when you are actually managing and weather prediction agency, you actually have a lot of things you need to take care. Like when you need to provide forecasts to citizens by running a numerical model, you usually use ensemble forecasting, like what we'll be doing in the project. So you have to have enough computer servers to run multiple copies of the atmospheric simulation. Usually the number of ensemble members is 20. And it is not desirable, more desirable, you have more members like 50 or even more. So you consider what budget do you have? Can you afford the operating cost of buying such numbers of computer servers? And also, what is the frequency you need you run a brand new NWP run? That is to say, if you run only a prediction run once only every day, it will not be satisfactory because say at night in the weather prediction report, you can only report the same thing as the forecast as in the morning. But as you know, if you run the numerical forecast simulations every hour with the latest initial condition you can get, then at night you can use the latest run, which hopefully is more accurate in predicting the coming future. So it is desirable to have higher frequency in running it. So from daily to hourly, it is consuming you 24 times computer servers you can afford. And also the length of forecast in each simulation run, if you only do the time integration for 3 days plus the spin-up period, then the job will finish earlier. If you need to simulate it for a 9 days period, as you see, it is nearly 3 times the computational resource needed. And then for each run, you need to design the configuration of the spatial discretization. For vertical layer, for vertical resolution, The number of vertical layers to use is usually from 50 to about 100. So you have a choice, and this already gives you a factor of 2 in using computational resource. And for horizontal domain size and resolution distribution, by distribution, I mean for WRF, it is the nested domain. How large is the 27 kilometer resolution domain? How large is the 9 km resolution domain, something like that. And for unstructured mesh, you can specify the transition zone, how wide is it? And for the refinement region, how large is it? So this is the spatial resolution distribution. So you may always want final resolution for a larger area that will consume much more computational resource. So you are given a fixed budget of computational resource. You will need to distribute them among these factors. So for NWP model, what we are doing is to make this horizontal resolution distribution to be more resource efficient. So it uses less computational resource in this factor. So for the fixed computational resource you have, you can spend it, you can redistribute it for other areas, you can put it to this dimension. So this is our intention when we try to modify MPAS to the so-called CPAS model with hierarchical time stepping and also the mesh generation.